So we've been talking about points to analysis, where we basically identify all the objects to which a pointer may point to. And this is, an objects may point to other objects and so on and so forth. And the question, however, is that in a program, the number of objects that are actually created may be dynamically created, may be unbounded. Here's an example of a program with an unbounded number of objects, and this is a simple program that creates a linked list. A node in the linked list is represented by struct L node, which contains a value v and a next pointer. And this is the code in a C++ like language that just creates k different nodes and links them together in a linked list. Now, in general, at runtime, the program may have an arbitrary amount of logic to that is preceding any allocation event. For example, here the allocation event is this new L node, but the number of times this new L node is called depends on the for loop, and the number of times the for loop iterations executes depends on this parameter k. In general, it is an undecidable problem to identify how many times a loop may execute, because the condition for the loop to execute may be arbitrary. And so in general, it is impossible to identify, or undecidable to identify, the total number of objects that a program may create at runtime. So the points to graph, the actual points to graph for this kind of a program would look something like this, where the head is the list head, because we assign the newly allocated node to n, and we do n.next equals head. So head points to the most recently allocated object, whose next pointer points to the second most recently allocated object, and so on until the oldest object, whose next pointer is going to point to null. And this is the actual points to graph. Notice that the number of objects in this points to graph is unbounded, because an unknown at compile time. What we need for our compile time analysis is that we need a predictable number of objects, or a bounded number of objects that we can reason about at compile time. This picture can be drawn at runtime, but at compile time we don't know how big this picture is or what the shape of this picture is going to be. So to tackle this problem, we define the notion of an abstract object. An abstract object represents a set of runtime objects. So for example, all the objects that are created for a given linked list may be represented by a single abstract object, and so on. And so it represents a set of runtime objects, and this set of runtime objects may be that a single abstract object represents may be of bounded size, and a size that is known at compile time, or it may be of an unbounded size, or a size that is not known at compile time. For our compile time analysis to work, we require that the set of abstract objects must be finite, which means that depending on how we categorized the runtime objects. So the idea is that for all the runtime objects that the program may create, we partition those objects into different abstract objects. So for example, all the objects that were created for the linked list can be one single abstract object. All the objects that were created for the binary search tree may be one abstract object, and so on. And the total set of such abstract objects must be finite. So whatever scheme you use to partition these runtime objects into abstract objects must ensure that the set of abstract objects must be finite. And a corollary of that is that a single abstract object may represent an unbounded number of runtime objects, because after all, the total number of runtime objects is unbounded. And if we are trying to represent them through a finite number of abstract objects, that means each abstract object may potentially represent an unbounded number of runtime objects. So here's an example of abstract objects. And in general, you can choose any partition of the runtime objects as long as you satisfy the finiteness property of the set of abstract objects. And so you can be creative about how you partition the runtime objects into abstract objects. Now, and I'm going to give you 3 different ideas on how you make partition, and these are just some ideas that that could be possible, and some of these ideas are actually popular now because they are practically usable and useful in real programs. But let us say that just because when we are discussing the linked list example, we were talking about how some object is the last allocated object, second last allocated object, or most recently allocated object, second most recently allocated object, and so on. And that's how we're reasoning about the points to relationship in a linked list. The only problem was we don't know how many such objects may be allocated. So maybe we partition these objects that are created in a linked list based on the time of creation. And we say that an abstract object AI represents the last KI runtime objects created before all the objects that were represented by A1, A2, A3, AI minus 1. To make this more clear, let's say this was a timeline of program execution. Then if I am at this, if I'm considering a program at this point in the program execution, then the last K1 allocations, maybe for the linked list, are represented by abstract object A1. The K2 allocations that were prior to these K1 allocations are represented by abstract object A2, and so on. And maybe the Kn allocations that were prior to all these K1 plus K2 plus Kn minus ..ks minus 1 allocations are represented by allocation or abstract object allocation N. And notice that K1, K2, K3, Kn are all finite numbers, but the total number of allocations may be unbounded. So we may say that all objects that were allocated before all these objects, K1, K2, K3, summation of K1 plus K2 plus K3 plus ..Kn, all the objects that were allocated before them, let's call them, have a single abstract object called A last. So in this scheme, all these abstract objects A1, A2, A3 represent a finite number of concrete runtime objects, but A last represents a potentially unbounded set of concrete runtime objects. And so this is what this is the mathematical meaning of each abstract object. For I belonging to 1.n, AI represents the last Ki runtime objects created before summation of Kj from j equals 1 to I minus 1. For example, if I look at A2, then A2 represents the K2 objects allocated before K1 objects, the last K1 objects. Or if I look at Kn, then it represents if I look at An, then it represents the Kn objects that were allocated before all the K1 plus K2 plus ..Kn minus 1 objects allocated, and so on. And then there's an abstract object A last that represents all the objects created before all these objects were allocated, which is summation of j equals 1 to n Kj creations. Now this is just some arbitrary idea of grouping together concrete objects, runtime objects, into a finite set of abstract objects, where each abstract object may represent a potentially unbounded number of concrete objects or runtime objects. Now let's look at how this recency abstraction, how well this recency abstraction performs. So this way of dividing or partitioning the concrete objects into abstract objects, I'm also going to call it the recency abstraction, where we abstract out the project, the runtime objects using the recency of their allocation. And so let's take this linked list example that we saw, which was the creation of a linked list using this for loop. In this case, we can say that the head pointer will, and let's say in our recency abstraction, we use these parameters where n is equal to 2, which means I'm going to track two different classes of recent objects, and k1 equals k2 equals 1, which means I'm going to say that, I'm going to keep track of the most recently allocated object, the second most recently allocated object, and all the objects allocated before the last two objects, and that will be the A last. And if I draw the points to graph for this program, notice that because I have now a finite set of abstract objects that is known at compile time, I can draw this graph completely. Also, if I had some kind of analysis, the best answer that I could get for this program is that head points to, at the end of this program, head would point to the most recently allocated object, which I'm representing by A1. A1, an object of type A1 or an object in class A1, in abstract class A1, may point to an object in class A2, So this is what this represents. An object in class A2 may point to an object in class A last, and an object in class A last may point to an object in class A last, right? So this is the picture, the points to graph, or the points to relationships between abstract objects for this particular program using the recency abstraction. Head may point to the most recently allocated object. The most recently allocated object may point to the second most recently allocated object through the next pointer. The second most recently allocated object may point to an object that belongs to the A last partition or class, and A last through its next pointer may point to another object within A last. Notice that we have, when we do this abstraction, we have lost some information. For example, here we are, this picture seems to say that it's possible for an object in A last class to point to itself. Whereas in the original program, that was not possible. An object cannot point to itself, it can only point to another object. But in this picture, because we have abstracted out the concrete objects into abstract objects, it seems like an object in A last may point to another object in A last, which includes itself. So using this, although abstraction helps us make the problem tractable, it also introduces imprecision, and that can be seen in this example. Okay. Further, while the recency abstraction worked well if the only program that was running, or the only function in the program was create list, but let's say there was another program called create tree that was going to create some nodes in a tree in some order, and there was some parameter depending on which it will either create a tree of 0 nodes, 1 nodes, 2 nodes, etc. And in the main function, let's say there were calls to these functions. For example, head equals create list and root equals create tree. Now, because create tree may create any number of allocations, and we cannot at compile time predict how many allocations create tree may make, at the end of this program, at this point, at the end of this program, it's not clear whether head is pointing to the most recent allocation, or is it pointing to the second most recent allocation, or older allocations than the second most recent allocation. Because depending on how many allocations were made by create tree, head may point to either the most. So if, for example, create tree didn't make any allocation at all, then head may point to A1, the most recent allocation. On the other hand, if create tree made exactly one allocation, then head may point to A2. If create tree made more than one allocations, then head may point all to A last. And so it's not clear whether, so the graph, the points to relationships now become less precise, because we using the recency abstraction, because at compile time it may be impossible or undecidable to figure out how many nodes will create tree allocate, and because of that, it seems that because of that imprecision, the compile time analysis, the May alias analysis may conservatively determine that, hey, head can point to, or the May points to analysis may conservatively determine that head may point to A1, or it may point to A2, or it may point to A last. And maybe because through some analysis you are able to figure out that the last node that is allocated in create tree is the root node. So maybe the analysis is able to figure out that root still points to the most recently allocated object. So root will point to A1. Either root will point to nothing, in which case it's okay, or if it points to something, then it will point to A1. Now, this kind of a picture is less satisfactory than the picture that we had in our previous figure, because here we don't have, the precision is much less. We are not able to reason about the fact that head, the structure of the data structure is completely lost. It seems like head can point anywhere, A1 can point anywhere, A2 can point anywhere, and so on. And this is not very precise and very useful for most applications. So while the recency abstraction was one idea on how you could partition the objects, we have seen a weakness of the recency abstraction, because sometimes it may not be possible to figure out how many allocations are happening in a particular piece, fragment of the program, in which case you have to conservatively assume that any number of allocations may happen in that fragment of the program, and that may cause spurious edges in the points to graph. This relationship between the points to relationships denoted by these edges is represented as is also called a points to graph, where the node if a node in a points to graph points to another object, then basically means that the value stored in that object, for example in this case head, may have a pointer to an object of type A1, and similarly a value stored in A1 may have a pointer to an object of class A last, and so on. Okay, so to resolve the problem of the recency abstraction, here's another idea. How about we use different types, depending on the type of the allocation, we group the different allocations into different abstract objects. So for example, all the objects of type L node will be represented by abstract object L node, and all the allocations of type T node, which is T node represents a tree node for the create tree function that I have not shown. We'll have a separate abstract class called T node that represents all the concrete objects that are allocated for T node at runtime. Now, if we use the type abstraction, it becomes much the points to graph for this program becomes much better, because it seems like head may point to L node, but head will never point to T node. Further, in L node through the next pointer may point to itself. Similarly, the root may point to T node, and the T node through the left and right pointers may point to other objects in the class T node. But neither T node may point to L node, nor L node may point to T node. Head will not point to L node, and root will not point to L node. Head will not point to T node, and root will not point to L node. So this is much better information than what we had in the previous points to graph. In the previous points to graph, it seemed like both head and root may point to the same thing. Here, at least, we have this information that head will not point to the same thing as root, or in other words, head and root will not alias at runtime through this type abstraction. However, none of these abstractions are perfect. For example, even in the type abstraction, let's take an example that where the type abstraction actually does not work that well. So let's say I have these statements x equals new capital X and y equals new capital Y. Now, because these two are different, X and Y are capital X and capital Y are different types, I'll have different abstract objects, capital X and capital Y, in my set of abstract objects, and my points to graph would look something like this. So if I do x dot f equals y, that would basically mean that inside the object small x, I can have a pointer to an object y, which is of type capital Y. So which means that small x, first of all, may point to an object of type capital X. Small y may point to an object of type capital Y because of these two new statements. And finally, because of this statement, x dot f equals y, a pointer inside capital X, an object of type capital X, or an object of class capital X, may have a pointer to an object of class capital Y, and that pointer may be stored in the field f. That information is not shown in the points to graph, but the point is that a pointer inside an object of abstract class X may contain a pointer to an object of that belongs to the abstract class Y, and that's what this edge here represents. Now, this is what the type abstraction gives me for this program, but let me make this program slightly different. So let's say I create another variable z of the same type capital Y as the original variable small y. And in this case, once again, because I use the type-based abstraction, it seems like small z can point to an object of type capital Y. So I draw an edge from z to capital Y. And let's say at some other point in the program, I say z equals new capital Z, and capital Z is, let's say, a different type. Maybe one is a derived type and one is a base type or something like that, in which case small z may point either to an object of class capital Z, or it may point to an object of class capital Y. And this is what a points to graph looks like in this example. Now notice that this points to graph has an imprecision already, because it seems like both y and z may point to the same object. In other words, star y and star z may alias, because they may point to the same object. Whereas if you look at the original program, it's very clear that there's nowhere in the program where z is being assigned the same, where we're basically assigning the same pointer in z which was actually held in y, and so this is an imprecision in the points to graph. And this imprecision is largely arising because of the abstraction that we have made, which is the type abstraction. Now, how can I, now how does this make things hard? Because let's say, there was another statement called z.g equals x. So in other words, whatever is z pointing to, in this case, z may point to y or z. Now that can contain a pointer to x. So which means y, an object in type y, because z can point to y, can now contain a pointer to x. And an object of type z can now contain a pointer to x. So these edges from y to x and z to x represent the possibilities created by this statement z.g equals x. Once again, these are imprecisions because after all, z couldn't have aliased with capital, z couldn't have pointed to capital, to the same object as small y. And now it seems like y can through y I can reach capital X. Whereas actually in the program, I can reach capital X through z, but never through y. And so these imprecisions are an artifact of the type abstraction. Similarly, if I have another statement said z.f equals y, then it seems like z can point capital Z, small z is pointing to capital Z, so capital Z can point to capital Y, and because small z is also pointing to capital Y can point to itself, and so on. And the more the edges in the points to graph, the less imprecise the points to graph is. I mean, ideally, the best points to graph is the points to graph which has as few edges as possible. Of course, the analysis is still sound, but still needs to remain sound. But the fewer the edges, the more precise the analysis. And it seems like we are adding a lot of spurious edges because of the type abstraction in this example. On the other hand, if instead of a type abstraction, I used another scheme to create this object abstraction, and this scheme is called the allocation site abstraction. In the allocation site abstraction, for each statement in the program, I label it with the corresponding PC. So let's say this allocation site is PC1, this allocation site is PC2, this allocation site is PC4, z equals new y. Notice that even though they are both allocating the same, an object of the same type, the allocation sites of the fourth statement and the second statement are different because the PCs are different. And similarly, z equals new capital Z is an allocation site 7. So my points to graph now looks very different for the same program, but with the allocation site abstraction. Here what I do is I say, because any object that is allocated at PC1 is represented by abstract object 1, and small x can point to 1, small y can point to allocation site abstraction abstracted object 2. Because of x.f equals y, because x can point to an allocation site 1 object, so 1 can now point to 2, and y can point to an allocation site 2 object. Because of x.f equals y, we can say that 1 can point to 2. And say z equals new y, so that means z can now point to an allocation site 4. Now this is the place where the precision improvement happens. Earlier in the type abstraction, z could have pointed either to 4 or either to, now z was pointing to y, and which was also pointed to by small y. But in this allocation site abstraction, z is pointing to 4 while small y is pointing to 2. And it's clear that z, whatever star z is, it cannot alias with star y because they're pointing to different abstract objects. So the allocation site abstraction seems more precise than the type abstraction in this example. Similarly, when we say z.g equals x, so whatever z is pointing to, which is 4, can point to whatever x is pointing to, which is 1. So if I draw an edge from 4 to 1, and say z.f equals y, so once again 4 can point to 2 this time because z can point to 4 and y can point to 2, so 4 can point to 2. And then say z equals new capital Z. So now because z equals new capital Z, this is the 7th allocation site number 7, so now z can point to 7. And now, because of these statements, because z.g equals x and z.f equals y, once I say that z points to 7, then I also need to consider these statements, and this is, I'm going to use a fixed point algorithm, a DFA algorithm to figure this out, that if z can point to 7 and z.g equals x, which means whatever z can point to whatever x can point to, then 7 can point to 1, and similarly 7 can point to 2 because of z.f equals y. And this is the final points to graph that is obtained by an allocation site abstraction. We're going to see an algorithm to draw these points to graphs automatically later on, but in this module I'm primarily interested in identifying the different abstractions and their trade-offs. So for this example, the type abstraction is less precise because it introduces more edges than the allocation site abstraction, which has less edges for and better or less. I guess I can't directly compare the number of edges because the number of abstract objects is also different in the two cases. But less aliasing relationships are possible in this points to graph than in this points to graph. For example, in this points to graph, star y cannot alias with star z, whereas in this points to graph, star y can alias with star z. Finally, for our linked list example, if I use the allocation site abstraction, then there were at least two allocation sites. One was the allocation site that was allocating an L node for create list, and there was another allocation site that was that may be a part of the create tree function that's allocating the tree node. And if I use the allocation site abstraction, the points to graph looks something like this. Head may point to an object allocated at allocation site 1. And an object allocated at allocation site 1 may point to itself through the next pointer. Similarly, the root may point to an object of allocation site 2, and an object of allocation site 2 may point to itself through the next pointer. And once again, this looks like a nice, neat graph that allows us to reason about several aliasing and points to relationships and rule out several may point to relationships. And so the allocation site abstraction works well for this example where there's both a list and a tree, unlike the recency abstraction, which didn't work that well. Here's another example. Let's say the create list function was called twice. Here's an example where the allocation site abstraction actually creates more imprecision than desirable. So because both head and head 2 are calling the same function to create the list, there's only one allocation site that's basically representing both the lists created by both the function calls. And so it seems like HD may point to 1 and 1 may point to itself, but also HD2 may point to 1 and 1 may point to itself. Whereas root may still point to only objects and allocated at allocation site 2. Now this allocation site abstraction based points to graph is still better than the recency based allocation points to graph, but it has imprecisions. For example, it seems to imply that star head may alias with star head 2, whereas we can see from the code that that's not true. So allocation site is working better for the examples that we have discussed so far, but even it has imprecisions, and we have seen one example of an imprecision. We're going to see ways to get rid of these imprecisions later on. In general, it is possible to combine the two multiple abstractions. For example, you can have, for example, the type abstraction may create a set of abstract objects a1.an. Let's say an allocation site abstraction may create yet another set of abstract objects, let's say b1.bm. Then you can take a Cartesian product of them, and that would be the total number of abstract objects to potentially get more precision than any single abstraction. As long as we obey the discipline that the total number of finite objects is total number of abstract objects is finite, any abstraction is okay. Of course, there's a trade-off between how many abstract objects we want to create. Even though they are finite, if we take Cartesian products, they can become exponential very quickly. And the precision, so the more the abstract objects, maybe you can get better precision, but at the cost of higher runtime of the points to analysis.